In this video, I'll be going over the domain and range of different types of functions. So let's start with some definitions. The domain of a function is the set of all real number inputs for the function, and the range is the set of all real number outputs for a function. Oftentimes we'll think of the domain as the x values if we're thinking about a function graphically. So what x values does the graph have values for? And the range is, we can think about that as the y values for a graph. And we need to be careful that we remember that these are only the real numbers. So we don't want to be concerned with complex numbers or the imaginary number I when we're talking about domain and range. So let's first look at polynomial functions. A polynomial function is a function that is in this form: a sub n x to the n plus dot 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 plus a sub 2x squared plus a sub 1x to the first, etc., etc. Now, this isn't a very useful definition probably for you, so let's look at just some examples of polynomial functions. So we have three different functions: f of x, g of x, and h of x. And notice for each of these, we have real number coefficients, so 5, 2, -1, -4, etc. We could have also had a fraction as a coefficient. We could have a square root as a coefficient. All of these are still real numbers. In other words, they have values that can be located on the number line. Also notice that we have whole number exponents. Okay, whole numbers are the positive integers, so these are like 0, 1, 2, 3, etc. Now, what this means is we don't want to have any negative exponents. However, we could have positive rational exponents as well. So we could have, for example, 4 over 3 here. We could have 5/7 as the exponent, and so on. So these are restrictions on a polynomial function. So let's look at three different graphs. And actually, these graphs are the original functions that I wrote down, so before I made any changes with the exponents or the coefficients. So with these three, let's figure out what the domain and the range are for the functions. So let's first look here at f of x. We want to find the domain and the range. When we have a graph, it's really easy to find the domain and range. For the domain, let's think about all the x values that this graph hits, and then for the range, let's think about all the y values. So to think about the domain, we want to see, all right, pick a point on the x-axis. How about right here, maybe 1/2? Does that graph hit the does that value 1/2 give a value of the graph? Yeah, right here. Okay, so that point is included in the domain. How about this point? This point would point to this point on the graph. Okay, so it looks like all the points in the middle here are part of the domain. If we go to the right, yes, we can continue hitting values, getting values on the graph. And the graph of this function just keeps going up and to the right and up and to the left. So no matter where we are on the x-axis, we're going to get values that hit the graph. So what we would say for the domain is all real numbers. And we want to write this in something called interval notation. And how we do this, if you took college algebra, you saw how interval notation works. So for all real numbers, we're going to say -infinity to +infinity. Now let's think about what the range is. Let me erase what we had here. So the range is what y values does this graph hit. So the smallest y value looks like it's about here, maybe -4.25. but then it goes all the way up to positive infinity. So for the range, we're going to say from negative 4.25 up to infinity. Now the negative 4.25, the graph goes through that point, so we're going to include that point in the range. All right, let's look at h of x. Now again, anywhere on the x-axis, that's going to give us a value on the graph. No matter where we pick, it's going to hit the x-axis. So here again, we're going to say negative infinity to positive infinity. For the range, well, what's the smallest value, smallest y value? Well, this graph keeps going down in the negative direction, and it keeps going up in the positive direction. So it goes from negative infinity to positive infinity. So in this case, the range, as well as the domain, are both all real numbers. All right, and then let's look at g of x. The domain here, again, anywhere we have an x value, it's going to hit the graph. So the domain here is going to be all real numbers. For the range, looks like there's no smallest y value because it goes all the way down to negative infinity. And then the greatest y value looks like, I don't know, 1.1 or 1.25, wherever that graph hits. So let's say 1.1, and we'll include that. All right, so hopefully you've kind of seen what a pattern is for the domain and range. And that'll give us a general rule. And for that general rule, we would say all polynomial functions have a domain of all real numbers. So anytime we have a polynomial function, the domain looks like this. So if you have a question, or a function I should say, and you need to find the domain, if it's a polynomial function, you don't need to do any other work. In order to find the range, it's really useful and sometimes necessary to have the graph. So it's good that you're able to find the range, but that won't always be asked. Next, we want to be able to find the domain for a radical function. Here are some examples of radical functions. Radical functions are functions that have a radical in them. Specifically, or more precisely, they have the x, the independent variable, under a square root symbol or a radical symbol. Typically, a graph that has a radical looks something like this. That's how f of x would look. It would be moved over 5 units to the left. G of x is going to look something like this. So it has a vertical stretch. H of x is a little more complicated. But the thing we need to remember about each of these is that when we have a radical function, the expression underneath the radical, this is called the radicand. This must be equal to 0 or greater than 0. So it must be 0 or a positive value. And if you think about this, well, looking at these first two graphs, these graphs only have y values that are positive. So the output for this function is always a positive value, or it's equal to 0 because these graphs are hitting the x-axis. So what we want to do is we want to take the radicand expression and figure out when that is greater than or equal to 0. So this first one, x minus 5, or square root of x minus 5, what we do is we take the radicand, x minus 5, and we set that greater than or equal to 0. Now let's solve for x. We get x is greater than or equal to 5. So if I was to graph this on a number line, what this is saying is x can be anything that's greater than or equal to 5. So it could be equal to 5, and then it is anything greater than 5. So if I was going to write this in interval notation, we would start at 5, and we're going to go all the way to the right to positive infinity. So we include 5 here because x could actually equal 5. That's what this inequality symbol is telling us. Let's look at the next one. We're going to set 5x greater than or equal to 0. Again, just set the radicand greater than or equal to 0. Here, when I divide both sides by 5, I actually get 0 over 5, which is 0. So what this one is saying is x can be anything greater than or equal to 0. So we're going to start at 0, and we're going to shade to the right. So in interval notation, this is going to be 0 to positive infinity. H of x is a little more complicated, but we're going to use the same process. We want to figure out when is the radicand greater than or equal to 0. So we're going to do this one a little bit differently. We're going to think about this graphically. So in order to graph this, if we had a graphing calculator, we could graph this. But if we want to do this by hand, what I'm going to do is I'm going to factor the left-hand side. I get -2, -3. So what that means is x equals 2, x equals 3. These values are going to be x-intercepts for the graph. So if I think about what this graph looks like, if I'm graphing this, x squared minus 5x plus 6, this is a parabola. It's opening upward because I have x squared. And what we have is x-intercepts at 2 and 3. So if I was going to graph this, I don't have to be very precise. I just need to know that this opens up and it passes through 2 and 3. Now we want to know where this graph is greater than or equal to 0. So if I look at this graph, it looks like in this portion of the x-axis, the graph is above the x-axis, so we're going to say that's positive. In between, it's below the x-axis, so we're going to say it's negative. And then to the right of 3, the graph is again above the x-axis, so it's positive over there. All right, so looking at this, if I think about this as the intervals, we're going to say negative infinity up to 2. The graph passes through 2, so we're going to include that. And then on the right-hand side, I have 3 to infinity. When we have two intervals, we use this symbol. This is called the union symbol. So the domain is going to look something like that. So from negative infinity to 2, union 3 to infinity. So this one's a little more complicated, but conceptually, hopefully by thinking about what the graph looks like, this gives you a better understanding of what the domain is looking like, because we want to know when this is positive. We can always figure out when an expression is positive by graphing it. So wherever that graph is above the x-axis, those x values would be making up where the function is positive. So as a general rule for finding the domain of a radical function, what we would say is the domain contains all values that make the radicand positive or 0. So in other words, set the radicand to greater than or equal to 0. All right, so that's how we find the domain for a radical expression. We're not going to worry too much about the range here, just because we will always need the graph to figure out what the range is. So that's not going to be our focus right now. Next, let's find the domain of rational functions. Here are some examples of rational functions. So a rational function is a function that has a polynomial expression in the denominator. So each of these in the denominator are expressions, simply put, that each of the denominators has x. So an easy way to think about this is that the denominator has the independent variable, which is usually x. Okay, so how do we find the domain? Well, when we're talking about any fraction, we don't want the denominator to be equal to 0, right? something like this, 5 over 0, we say is undefined. So we want this function to be defined. So what we want to do is find out when that denominator is equal to 0. So to do that, what we do is we just take the denominator, set it equal to 0, and then we solve. So for f of x, we would say anything except for 7 is going to, in other words, it's going to work in this function. 7 will make the function undefined. So if we think about this on a number line, anything except for 7 is going to be defined. So I put an open circle on 7, and then we can shade everything else. So everything else is in the domain. So this domain would be negative infinity to 7. This time we do not include the 7, because 7 will make this undefined, so we put a parenthesis, and then we say 7 to infinity. All right, so that's about as easy as it would get for a rational function. For the second one here, we want to, again, set the denominator equal to 0 and solve. To solve this equation, this is a quadratic equation, we could use the quadratic formula. We could also try to complete the square. However, this one factors, and when a quadratic can factor, that's the route we want to go in, because things will go a lot quicker. So the question we want to ask is, what multiplies to negative 12 that also adds up to negative 1? And the numbers that do that are negative 4 and positive 3. Set each of these equal to 0 to solve. So we get x equals 4, and we get x equals negative 3. So what this means is, anything except for these two values are going to make this function defined. So we're going to put open circles on those two values, and everything else is in the domain. Okay, so this domain is going to have three different parts. We're going to say negative infinity to negative 3, union, negative 3 to 4, union, 4 to infinity, and that will be the domain. You don't need to do this on the number line. I'm just drawing the number line because hopefully it helps make a connection between what we get here, and then the number line helps us visualize that, and then writing the interval notation once we have the number line, I think is helpful. All right, let's move over to h of x. This one's a little bit more complicated. So we still want to figure out when this denominator is equal to 0. So we're going to say square root of 3x plus 6. When does that equal 0? However, because this is a radical expression, this radical expression must be positive. So in other words, let's say I had 8 over the square root of 0. We can take the square root of 0, it's just 0, but then we're going to end up with 8 over 0, which is undefined. So we actually don't want 0 in the denominator. So we just want to figure out where that bottom is going to be a positive number. It can't be negative because then we couldn't take the square root of it. So maybe I should write it like this. So initially, if we have a radical, we want to know when is that greater than or equal to 0. However, we don't want this to be equal to 0. So what we're going to do is we're just going to say 3x plus 6, when is that greater than 0? So when is that expression greater than 0? So to solve this, we get x is greater than, just greater than negative 2. All right, so on the number line, we have 0, we have negative 2. Because this is just greater than, we're going to have an open circle on negative 2. Greater than is going to be shaded to the right here. So in this instance, we're going to say the domain is anything above negative 2, but not including negative 2. And so let's just check this. Let's pick a number maybe over here. How about negative 3? If we input negative 3 into the denominator, we're going to get the square root of 3 times negative 3 is negative 9 plus 6. We end up getting negative 3, which we can't take this, we don't take the square root of and get a real number. So this domain seems to be correct. So as our rule, we can say that the domain contains values that do not make the denominator equal to 0 or undefined. That's what we did over here in h of x. We had to figure out when was that also going to be undefined because of a radical. So in other words, we solve for d of x equals 0. D of x is just shorthand for the denominator. Denominator. All right, lastly, we're going to talk about piecewise functions. A piecewise function is a function in which more than one formula is used to define the output. The domain is the union of each individual domain. So let's look at an example of a piecewise function. We would say f of x is equal to x squared when x is less than or equal to 1, or 2x when x is greater than -1. I think I needed to put -1 here. Okay, so we have two different formulas or rules. Okay, so we're going to say this function uses x squared when x is less than or equal to -1. It's going to use 2x when x is greater than -1. So let's figure out what the graph of this looks like. Let's evaluate a few different points. F of, how about 0, f of -1, f of -2, and then let's find the domain. And since we'll have the graph, let's also find the range. All right, so let's go ahead and graph this piecewise function. So it looks like the restrictions for each of these functions has a cutoff at -1. So at -1, for this rule, we're going to say x squared anytime x is less than -1. So in other words, if we're to the left of -1, we're going to use the function x squared. When we're to the right of -1, we're going to use the function 2x. All right, so let's see what happens when I plug in -1 into the first rule. So -1 squared, that's going to equal +1. So at -1, I'm going to get a value of +1. Let's say -2. When I plug -2 in, I'm going to get -2 squared, which is 4. So at -2, I'm going to get +4 right here. And then if I do -3 squared, I'm going to get 9. So at -3, I'm up here. So what this looks like, if we know kind of what this graph looks like, it just looks like a parabola. Let's try. So it's going like this. Now, we know that a regular parabola looks like that. However, because this restriction is saying x, we only have the parabola for x less than or equal to -1, that means we're going to get rid of all of this over here. All right, and then for the second rule, we say f of x is equal to 2x when x is greater than -1. So a number that's greater than -1 would be 0. So 2 times 0 is equal to 0. 1, 2 times 1 is equal to 2. 2 times 2 is equal to 4. So plotting some of these points, 2 at 0, at 1 we get 2, at 2 we get 4, and so on. We know that this is a straight line, so it's going to go like this. Now again, a regular straight line is going to go on forever. However, because we have a cutoff at -1, we're going to get rid of that portion. And it actually goes down to -1, but it's not going to include -1, so we're going to put an open circle right there. And remember, a function must pass the vertical line test. So if I draw a vertical line there, it is only hitting the blue portion of the graph. The right portion of the graph is an open circle there. So at at -1, the graph still passes the vertical line test. All right, so this is what our graph is going to look like. We also want to figure out what the value of the function is at 0, -1, and -2. Well, I think we already have that. 0 is here, -1 is here, -2 is here. So let's just summarize here. So f at 0, when the function equals 0, that's this point right here. So that's 0. And if we just have the algebraic function and we don't have the graph, well, 0, if you're trying to figure out which of these rules 0 should go into, just plug in 0 in for each of the x's. Is 0 less than or equal to -1? Or is 0 greater than -1? Which of these is true? Well, this one is true. So that tells us we're going to use the second rule, and we're going to plug in the 0 into 2x. So 2 times 0 is how we get the 0. F at -1. Okay, so again, which rule? The first rule or the second rule? -1 is going to satisfy this inequality because -1 is less than or equal to -1. So we're going to plug it into the first rule, and we get +1. That on the graph is this point right here. And then f of -2, again, that's going to be the first rule because -2 is less than or equal to -1. So -2 squared is equal to 4. -2 is going to be this point right here. All right, so now let's find the domain and the range. Well, looking at the graph, if we start over here on the left-hand side, the blue graph keeps going up and to the left. And then at -1, the function jumps down to the red portion when we're above -1, and then the graph just keeps on going to the right. So the domain here is all real numbers. Every x value has a corresponding y value on the graph. And then for the range, let's think about what's the smallest x value? Well, what's the smallest y value? It looks like it's right here. It's close to -2, but it's not exactly -2. In other words, it doesn't include -2. But then from there, it looks like the y values just keep increasing. So the y values go to +infinity.